My name is John Matthew Holt. It's nice to be here in Orlando. I flew in from Ireland, which is where I spend a lot of my time, and the weather here is certainly a lot better than it is from whence I came or from where I came. The subject for the next hour or thereabouts is to talk about code injection attacks, code injection vulnerabilities, and I guess view that problem through two lenses. Number one, how we as an industry, how the security industry has been responding to and dealing with these types of attacks up until the present. And then in particular, what kind of techniques are emerging for responding to these types of attacks going forward. And it seems like a pretty timely topic to talk about. I'm sure everybody is hearing more than they want to or need to hear about Equifax, but code injection vulnerabilities, of which deserialization attacks and struts is an example of that, all fit into the same box and the same bucket. So it's a timely conversation. Now, it's going to be a different kind of conversation because I guess I'm not a normal security guy. In fact, to be honest, I'm not a security guy at all. My own background personally is I'm a compiler engineer. I have spent specifically over a decade working on the just-in-time compiler for the Java Hotspot JVM and several others. So that's my background. It's the background of most of the team that I work with in the company I come from, which is a company called Warratec. Now, security folks might ask me, what does a compiler engineer, specifically a just-in-time compiler engineer, have to say about code injection attacks? But just stop and think about it. We should have quite a lot, because the root issue of a code injection attack is external user input or external users finding a way to inject functional code into your application. Through whatever means or vector that might be. At the end of the day, that means that code is going to have to be compiled. And that's when somebody like me comes into the conversation. So I'm going to be talking through this subject matter as a compiler guy. I'm going to be reviewing the state of the art in responding to code injection vulnerabilities and code injection attacks as a runtime engineer views this. And then I'm going to comment about the techniques that the runtime engineering community and the compiler community are starting to bring to bear and apply on this problem. Because I guess the opening comment I make about this topic matter generally, it is striking that something that is so important and significant, like code injection vulnerabilities, and the application securities community's response to them, has never reached across the aisle and invited the likes of myself, compiler guys, to come to the table and join that conversation. Expressing it kind of in a tongue-in-cheek way, when I walk on a security floor into an exhibition hall like here at OWASP, here at AppSec, or at RSA in San Francisco, when I'm standing on that exhibition floor, I stick out like a sore thumb. Because the terms you guys use as security folks, the techniques you try and apply to what are fundamentally code problems, if you were to come up to a runtime engineer or a compiler engineer like myself and suggest these ideas, we would respectfully chuckle and say there are better ways we can solve this problem. So it's an important topic, but it's important now because it's timely and because we need as a community to reach out to the runtime engineers, to the compiler engineers who are going to help us start to tackle this and take this kind of vulnerability and these kind of exploits off the table entirely. So, very first, we're going to look at how people have traditionally in the security industry been dealing with code injection vulnerabilities. We'll look at advances against protecting against code injection vulnerabilities that are coming from the runtime community, from the runtime and compiler community. We'll discuss about some of the most frequently employed attacks, some of the sophisticated ones. We'll talk a little bit about unvalidated bytecode attacks in the JVM, and so on, and then look at state of the art going forward. Now, I'm going to focus this conversation in the examples I give on Java, but the topic and the techniques and the problems are generic. At the end of the day, it doesn't matter what syntax or what grammar it is, whether you have curly braces or you don't have curly braces, whether you're white space indented or you're not white space indented. It doesn't matter what the grammar is. There's a compiler there, there's a runtime there, and that's a place where you can fix these kind of vulnerabilities. So I'll use Java because it's the most popular language, most people know it, but the techniques are portable and generic across. So just a quick recap, and I guess I can be a bit controversial here because I'm not a security guy, so I'm going to say things that maybe security folks won't like, and that's fine, you can beat me up for it. I hear this a lot. In an ideal world, we would all write good code. And we should. Oops, we have got autoplay on. And in an ideal world, we should. We should be training our developers, we should be giving them tools, we should be giving them courses, we should be giving them testing systems to help them write the best code that they possibly can. But we shouldn't be relying on them. And my perspective as a runtime engineer on the application security problem, code injections and others, types of vulnerabilities, my perspective is that this is deja vu for a runtime guy like me. And this is what I mean when I say that. For the folks of you in the room who are old enough, I just am old enough. If we cast our minds back to the early 1990s and compare the early 1990s to today, we see that the industry is going through something of a similar process now. And what I mean is as follows. If we were to take a snapshot of the ticketing systems of applications today, open up Redmine or open up Jira or whatever ticketing system you use, go through all the individual bugs and issues and put them into buckets of relatedness or related issues. Do the same thing for application projects in the early 1990s. There will be a very large bucket that is now conspicuous by its absence. A large bucket of bugs that in 2017 virtually don't exist, and yet in the 1990s were one of the largest, if not the largest, box of bugs or buckets of bugs at the time. Now, a security vulnerability is nothing more than a software bug. And maybe some people can guess what I'm referring to here, but the bugs in the box of bugs that disappeared between 1991 and 2017 are memory leaks, double dereferences, memory bugs. Something happened. And in fact, something happened pretty quickly. You have a look at the ticketing systems in the early 1990s and you spit out all the bugs that were in those ticketing systems, memory leaks would be a large part of them. Fast forward the best part of a decade, the people coming out of university, the college students now, don't even know what they are. Something happened and took them away, took them off the table. And the answer, of course, was the word that we don't like, garbage collectors. Automatic memory management. Or to express it in runtime engineering terms, let the runtime engineers solve your application problems. Now, nobody adopted a garbage collector because it made their application run faster. They adopted garbage collectors for one reason, and the reason's a bit surprising. They adopted garbage collectors because they are accurate. Garbage collectors never make a mistake. They don't forget to collect an object and leave a little gathering dust of objects in your memory. Garbage collectors don't collect the same object twice. If a garbage collector makes a mistake, seg faults. It became more economical the moment automatic memory management could provide a deterministic guarantee of accuracy. It became more economical for the runtime to do it in spite of performance cost. If we look at security problems today, code injection a good example, so long as the runtime, or when the runtime engineers can step into the conversation and push the deterministic guarantee that they can provide above that accuracy threshold, where they can say, I'm going to catch this issue and I'm never going to make a mistake. I'm never going to do a false positive. Then you get the same economic advantage. Economies of scale advantage. It is more efficient for the runtime to do it than for human beings to chase those bugs. So yes, human beings should be catching more code, writing better code. Our formatting looks like it has been a bit lost. Human beings should be writing best code. They're not going to. We shouldn't be relying on them. And just some statistics to give some numbers around the size of the security problem. This likes to autoplay forward. If you take the Java platform, we all talk here about our OWASP vulnerabilities. We think about SQL injection and cross-site scripting and cross-site request forgery and so on and so forth. Just pause for a minute and think about the platform that your application is running on. If you've ever sat down and computed the frequency with which Oracle finds and fixes a vulnerability, including deserialization vulnerabilities, in the core Java platform APIs, the current, and it has been for years, average find and fix rate is there's a new JRE vulnerability every 100 calendar hours. So you can be paranoid about your SQL injection, you can be paranoid about your Apache struts, but in January this year, 2017, Oracle fixed a core unsafe deserialization vulnerability in Java.io.objectInputStream. If you're going to be serious about dealing with code injection vulnerabilities, you have to look at the whole stack. And that's important because as you go lower down the software stack into the runtime platform itself, the community of engineers, again, that you need to start to tap and invite to help solve that problem, and not the traditional security guys, they're the runtime guys. Security tools, do we have all the security tools we need? Well, we probably have quite a good number. The tools is not the problem. Finding the issues is not the problem. The industry's problem is fixing them. We can find more than we can fix as human beings. Oh, this just doesn't stop. We can find more than we can fix. So it's not a tool problem. It's a remediation problem. It's a response problem. Now, this is one which I like talking about. I don't like this word. And I'll put a context around it. There's the context there, if I can pause it. That's what Wikipedia defines as heuristic. Now, if you had to pick a word out of the dictionary that you did not want to appear in the same sentence as the word secure, that's a pretty good candidate. Let me just read the bits in red, right? Heuristics are things like pattern matching, things like regular expressions, things like whitelists and blacklists. These are keywords used by the security industry, and unfortunately, when we talk about code injection vulnerabilities, these are keywords used for code injection vulnerabilities, which to a runtime engineer like me, we scratch it, what are these people thinking? But here's the definition of heuristics. Finding an approximate solution. What a horrible word. Approximate does not belong in a sentence that has security. When classical methods fail to find an exact solution. There's only one type of solution you want for security purposes, and that's exact. It trades optimality, completeness, and the keyword accuracy for speed. And the last one, the real kicker. Guys, if you're using pattern matching, if you're using regex, if you're using whitelists, you're using blacklists, it's a shortcut. You're not solving the problem. It's a shortcut. So, I present these as facts. Sometimes people argue and challenge, but they're pretty practical. We need to teach our developers to write better code, absolutely. Give them all the classes we can, give them training programs, conferences like this are key. Give them all the tools in the world, that's key. But we shouldn't be relying on them as our application security strategy and relying on them as application security posture. Another thing you need to start to think about, and this is a runtime engineer speaking, when I sit down and profile an application, I take that bit of business logic, which to the developer that wrote it, he thinks that's the world, right? That's his cosmos, that's his universe. His little bit of business logic, his banking application, his sales or retail application, to him that is the most important thing in the world. Guess what, sweetheart? When I profile it as a compiler engineer inside the runtime, you are lucky if the instructions and the source code that you are writing is scratching 20% of the clock cycles on the CPU. It's an iceberg, and you're dancing on the top. That's why things like the Java platform APIs themselves have unsafe deserialization vulnerabilities. So you may have the best policy in the world for patching struts, but if you're not patching Java, you're not fixed. And then finally, patching itself is a problem. I mean, we have a bit of a joke. When I go and speak to customers and I go and speak to people who are dealing with the application security problem of Java or .NET or any other applications, I'll put it in the context of Java. I walk into the room of large organizations and I say, well, which versions of Java are you using? And the answer is yes. All of them, literally. Right? Patching is a problem. Now, if we could patch, if Equifax could patch, we wouldn't have a problem. But it's just such a burden. And organization struggle. So it's these combination of three things. These are, I guess, truths that if we start to accept and understand, we need to be looking for new techniques. We need to be challenging the systems we're using, because clearly the way we're trying to solve these problems right now is not working well. So I'm going to switch to the second part of the conversation. I'm going to jump around now and talk about some different approaches to dealing with these issues that come from the runtime community. And these can be quite deep and quite advanced. So I guess to set the context here, my background, and I'm going to kind of a little spiel on myself now in this context in the company I work for. Warratech's a bit unusual as a security company. We have a stand next door, so please come by and see us and we can chat. We're not a security company. I'm not a security guy. My team are not security engineers. We're runtime engineers who realize that the kind of problems that people want to solve in application security are only going to be solved well in the runtime. And so as a team and as a group of people, when we start to step in to deal with the security vulnerabilities, we all talk about the OWASP top 10 and whatever different vulnerability types and categories we want to talk about. When a runtime engineer walks into that conversation and enters that narrative, he is availing of techniques and he is availing of tools in his toolbox that are generally unknown to the security community and the security teams, at least in an efficient way. One of them is this. There's quite a lot of talk, increasingly. It's not a new idea. The key word here, which I'll talk about a little bit, is the word tainting. A runtime engineer like myself, I have a slightly different way for describing this, and I'll talk about that, and that's tracing. And there's a slight difference. The idea of tainting is as old as the hills. It's been used in different languages to varying degrees of testing success. And I emphasize the word testing. The idea of tainting is quite simple. Identify input that comes from outside the application, kind of follow it where it goes inside the application, and then when you see, so the simple hypothesis goes, when you see external input that comes from some untrusted source appearing in a sensitive operation, jump up and down and wave your hands. And that's what traditional tainting systems have done. And that's good for testing to some degree. It can red flag things that you may not know. It can tell you that particular functions and sensitive operations that you previously trusted and didn't know to be suspicious of have some security risks or problems associated with it. Now get a runtime engineer, specifically a JIT compiler engineer, to walk into that conversation. There's one thing that has always been a problem with tainting. I think there might even be another talk here that mentions one of these problems. People think that tainting is expensive. Computation, performance. Who's the best community in the world to deal with performance problems? Compiler engineers. In fact, it's our bread and butter. There's one thing we do very well, and that's optimizing code. So the value that tainting can provide, which is the identification of data origin, not the enforcement of security, the identification of data origin, has traditionally been thought of and has traditionally been attempted in naive ways, resulting with performance problems. When you reach across the aisle and you bring in a runtime engineer or a compiler engineer and you say, listen, I want to identify origin of data and memory. If I'm able to do that, imagine we're in Disney, right? Imagine a world where there was no performance cost. If I had that capability, then I could start to bring some other techniques, like lexical analysis, and I'll talk about that, to then start to deterministically detect certain types of code injection. The lexical analysis bit, that's actually really easy. The tainting bit is what people have traditionally thought of as hard. But you reach out to a runtime engineer and a compiler engineer, you say, listen, I need you to come back with a technique that can do tracing and do it well, and do it low performance, low overhead, high performance. Then suddenly you start to unlock a new technique for dealing with certain classes and categories of code injection vulnerabilities. So tainted lexical analysis was one of the very first techniques that me and my team started to apply. There's nothing particularly unique about it. It's based on runtime and compiler techniques that are really quite well established. But it requires tracing and it requires it at high speed. And as compiler engineers, we do that very well. And the concept is really quite simple. If we can reliably identify data origin, we can then start to apply compilation techniques based on syntactic and lexical analysis to identify when code injection conditions occur. Now, that's shorthand for a bunch of complicated compiler techniques under the covers. But the results are simply this key word. It detects them deterministically. No tuning, no pattern matching, no regular expressions, no whitelists, no blacklists. Deterministically from the very first SQL query, from the very first HTML construction, if it's cross-site scripting. When you can link two techniques the security industry has not had at its disposal before. Real-time memory tracing at 1 to 2% real performance cost, real numbers, and lexical and syntactic analysis with taint information to identify data origin. So an example of kind of extreme stuff. Now, the consequence of this, just to give some context, I'm not going to go into this in too much detail. There's a couple of things I want to cover. This stuff is real. The products that I build and work on, I've had this in live production now over 2 years, running hundreds and hundreds of applications, unconditional blocking mode, and to this very day, never, ever, ever, ever had a single false positive. Remember, what was the threshold that garbage collectors needed to cross to make it more economical for the runtime to do the work than human beings? It was accuracy. The moment the garbage collectors didn't make a mistake, they didn't forget about objects in the corner, then it made more sense for the human beings to let go of that problem and let the runtime deal with it. The same thing applies for security vulnerabilities and security bugs. The moment the runtime can put its hand up and say, I got this, and I've got this with no false positives, and if I'm wrong, I'll give you $10,000, you've crossed that threshold, and that category of vulnerability goes away. Solved. So SQL injection, cross-site scripting, path traversal, directory traversal, XPath injection, reflection injection, command injection, bash injection. Taint lexical analysis. Takes them off the table, zero false positives. So an example of what the runtime community can start to bring to the security community solving application security problems. Another one, this one perhaps a little bit easier to visualize because we can put it in the screen and show it to you visually. That abbreviation, some people might cotton on and they might say, oh, hang on a minute, NSLR, that rings a little bell. Doesn't that sound like something called ASLR? So we're shifting to a different type of code injection vulnerability now. Bytecode injection. Getting class files, in the case of Java, injecting class files into an application, a bit different to the SQL injections, a bit different to the cross-site scriptings of path traversal, which are a form of code injection, but different. This is dealing with unvalidated bytecode attacks and attach API attacks for Java. Now, as a runtime engineer, when I started to care about security of the JVM, I get very embarrassed in the early days because the JVM is a sieve. The JVM has no concept of security. It has a thing called a security manager, doesn't really work. It has no security controls, and so long as you can get some bytecode running on that thing, if you tell the JVM to delete a file, it's going to delete a file. You tell the JVM to fork a process, it's going to fork a process. Tell the JVM to open up an outbound TCP connection somewhere, modify a SQL statement, it's going to do those things. So the problem is then the JVM has no controls and guards for bytecode or class file injection. Now, it's an interesting problem because as a runtime engineer, when people started to communicate, hey, this is a type of code injection vulnerability, we're concerned about this, we don't have good techniques to catch this today, we try and do whitelists and blacklists, and we try and allow that class but not allow this one. Well, whoa. Let's understand the problem. The problem is that the attacks are deterministically predictable. Now, as a runtime engineer and as a compiler guy, looking around the runtime community for similar problems, there's another community, runtime community, that solved a similar type of problem to an unvalidated bytecode injection attacks or class file injection attacks in a slightly different way. And that's the operating system folks dealing with buffer overflows. Now, first, when I make that statement, some people jump up and say, well, hang on, what's buffer overflows got to do with class files and bytecode? They both inject code. Buffer overflow just rolls over the end of a buffer or underflows the buffer, injects a series of ops into the CPU, gets the CPU to jump to that particular instruction, and whoopee, you're on your way. That's no different to a class file. Now, the runtime community from that side of the operating system runtime world came up with quite a clever technique. It's pretty good. It's not perfect, but it's pretty good. And that's called address space layout randomization. It's based on a very simple premise. That is, hang on a minute. If we make memory layout non-deterministic, and attacks by nature are deterministic, then it makes it computationally infeasible to be able to know jump locations in memory for reliable gadgets and functions that you need to chain together to do something useful. Okay. Why couldn't we bring that to the runtime for applications like Java? If you do, you're going to change it a bit. Because as everyone, I think, in this room would probably know, Java's not like C. You don't have direct access to memory. You don't have pointers. So you're not talking about memory addresses. You're talking about names. Namespaces. And just stop and think about the example at the bottom of this slide. If you're an attacker and you want to inject some bad code, some bad class file into a JVM that's going to run some malicious functionality, various ways you can get that into the JVM. Java is based on a type system. It's strongly typed. And at the root of all of those typed classes is Java-lang object and Java-lang string and others. If you want to do anything useful as an attacker, you're going to kind of have to make use of Java-lang object. And you're going to have to kind of make use of Java-lang string. And probably a bunch of other things. Java file, Java-lang process builder, people love that one. Take them away. Make them not deterministic. Now, that raises a whole bunch of runtime problems about how on earth you let software actually run and continue to operate without breaking. But just put that to one side for a moment. If you can randomize the namespace of Java itself, you don't need to randomize anything else. You don't need to randomize com.mycompany.blah. You don't need to randomize org.apache.something else. If you just randomize java.something so that Java doesn't exist, and it changes every time you reboot the app, you're going to make it really difficult to do bytecode injection and class file injection attacks. Because that thing, that java.lang.system, that java.lang.process builder that you want to use doesn't exist anymore. So this is something that has now been around for nearly a year as a technique that the runtime community has been starting to provide and apply. There's an example. Now, some people, if you're a Java developer, you may even recognize that. That's a Java process running on a Linux box, and you go kill -3. That's a dump stack. Have a look at the magic yellow box. That changes every single time you restart that app. But what's more, so Java $, dollar is the convention in Java for synthetic. So $, 96-bit random number in hexadecimal. Or basically variant of base 64. But here's the kicker. If you're inside the application and you go java.lang.throwable.getStackTrace, get class name, it's not random. If you go java.lang.classloader.load class in certain situations, it's not random. So the security benefit of this is pretty clear. That's easy to understand. The complexity comes how on earth do you make it work in the runtime? And how do you do it in such a way that the application doesn't break? That's where the complexity comes in. Now, the community that needs to deal with those kind of problems are the runtime folks. The guys in the JIT compiler, the guys in the compilation pipeline, the garbage collector on the runtime, and the JRE. If you can solve those problems, which are hard, but if you can solve those problems, then you can start to bring randomization from ASLR but apply it to namespaces. And once again, lift and take off a category of vulnerabilities off the table and drop them. So this becomes the repeating drumbeat of runtime engineers stepping into the room, is the techniques that they bring really come left field to the security folks like this. And when you apply them correctly and when you incur the engineering cost and effort to do so, then just like garbage collectors took away a whole category of bugs from our ticketing systems in the 1990s, these runtime security solutions can take away a category of security vulnerabilities so that the people coming out of college in 5 years' time will read about this in the history book and chuckle themselves because they've never seen it in real life. That's the recurring pattern. Here's another example just to illustrate it for people in the Java world. Same thing. This is an example of actually using it to control things like the JAttach or the JNI invocation API, instrumentation API. You try and attach to the Java process, it's going to go ahead and try and access particular object types. If you don't want it to, you can tell the runtime security control, don't let that happen. Connection failed, because it can't make sense of the namespace it's attaching to. Pretty extreme stuff, pretty cool. Kind of a third example, and I guess this now is more timely, particularly in light of all the focus and attention around struts and the news stories that have been linked to that. Another example of a technique from the runtime community coming in to tackle a different class of code injection vulnerabilities. So this is now hardcore down deserialization path. It affects other vulnerability types as well, but probably deserialization, unsafe deserialization is the hot topic right now. And that is applying the concept of de-escalation. What does that mean? Well, think about it. Modern applications, it's that dancing on the iceberg example or metaphor I gave at the beginning. Modern applications are made up of parts, and you don't write them. You write a small amount, 20%. And then you import a whole bunch of otherness, other stuff from other people, which provides a service or a capability or a facility according to some well-defined, well-understood API or conventions. Components, libraries, jar files in Java, whatever term or description we want to use. What's really nice about modern software composition and modern application development that uses these kind of easily identifiable, reusable software components is that the contracts of behavior can be inferred against the component, and then we can start to define in the runtime, or teach the runtime, to understand the boundaries of components, and that when you're inside one component, these are the certain constraints for how you should operate, how the runtime itself should operate, and when you're not inside that component, there's a different set of constraints. So it's recognizing that applications are composed of these modular parts, and the modules themselves are easily and consistently identifiable, and secondly, that the modules have, in most cases, fairly well-defined and fairly well-boxed, shaped behavior, where you can define contracts around that or conventions, and then you can identify when those conventions are being broken or some out of normal behavior is taking place. So this is something that's pretty cutting edge going on right now in the runtime community. A lot of excitement here. This is also a variant based on similar techniques in the operating system community. This is kind of hot topic, hot focus for runtime security guys. Looking at the idea of de-escalating components and saying, okay, let's identify the boundaries of these modules, and then let's find conditions and cases for modules where we can say module X should only have a reduced set of, I guess you can call them permissions if you want to think of them that way, a reduced set of permissions, and then make the runtime the enforcer of that. Now, some people who know the security manager in Java might say, oh, this is a little bit similar to what the applets and security manager, conceptually, yes, but don't use a security manager. It's never going to work. But same concept, but applied differently. Apply it in the compilation chain, apply it inside the runtime itself. And you start to get different effects. Here's an example. Deserialization APIs are great fit for this. Deserialization is well boxed. Its behavior is well defined. If you think about java.io.object input stream, it has one public method of note. It's called readObject, and it returns you a single object, the root object of whatever deserialized graph it's constructed. And if you just sit down with a piece of chalk or a whiteboard marker and write down on the board, what is the contracted behavior that you expect from readObject? What are the kind of operations that readObject should be or should not be performing? Think about it. Basically two things. readObject should be allocating objects and linking them together in a graph. That's what readObject should be doing. readObject should not be computing Mersenne primes. readObject should not be forking operating system processes. readObject should not be doing a whole bunch of things other than allocating objects, and linking them together in a graph. So a very good example of an API that has a well-defined contract is part of some component. In the case of the object input stream, it's the JRE itself. You can think of the JRE as a component. In the case of struts, it's going to be the struts libraries for their own convention of doing deserialization. But it's a contract. And that contract is to return you a structured form of something. Okay, well then let's teach the runtime that when that begins, that's kind of all it should be allowed to do. If you start to enforce that in the runtime, then you can start to do things like this. My formatting's been lost in the PowerPoint, but you get the idea. What's beautiful about applying compartmentalization, or probably the proper word, micro-compartmentalization, to components like this. Once again, no heuristics or heuristics. There's no blacklists, there's no whitelists, no config or profiling or tuning. I mean, I've had some interesting conversations with folks who have been trying to make use of or trying to protect applications that have some form of deserialization operations using the state-of-the-art available right now, and they are being expected to somehow work out the dependency chain of all the types in the encoded object graphs. Like, oh, do we need hash maps, and is it an array of hash maps, or just a single, is it a one-dimensional array of hash maps, or is it a five-dimensional array of who knows, right? Even for me as a runtime engineer, it's going to take me a long time to sit down when somebody says, oh, you know what, I want you to protect that particular API call that's doing deserialization, and I want you to do the whitelist or the blacklist on that so that it fits this particular application. Okay, you can do it, but even for me, that's hard. That takes a lot of time. And if you just miss one little thing, snap, you're going to break the app. So, once again, what can the runtime do? Well, let's put that operation in a box. Let's define rules about how that box should work. And then let the runtime do it for us. Because if you think through the vulnerability types we're talking about and the recurring theme all along the way, there is one place in the world for every application where everything is known, where every memory read and write is known, where every instruction is known, where every function call, where every file operation, every database query, every input-output operation. It's not the network, it's not the firewalls, it's not the scanning tools, it's not the source code analysis, it's the compiler. The compiler is God. And for most contemporary languages, in fact since the 1990s, most, not all, most contemporary languages all have one thing in common. They're all built on a just-in-time compiler. God lives in your box. And God can solve this problem. Very exciting stuff. And kind of a final point, showing, I guess, how hard and how far you can push this kind of stuff. So I'm going to give a concrete example here. The key is accessing and exposing the intelligence, the capability, the facility of the compiler inside the runtime. Take it out of the closet. Take it out of the dark. Put the spotlight on it and let it shine. There's a star in there. And when you do that, you start to then get very interesting extensions of what that compiler can start to do. So what we've talked about, and we've done 3 examples of kind of new runtime engineering, runtime security approaches to code injection vulnerabilities of different types, SQL and cross-site scripting, Partraverse, and XPath injection, and so on, one class. Secondly, bytecode injection, unvalidated bytecode injection, class file injection, attach APIs, that's second class. Third class, unsafe deserialization. When you have now a runtime that starts to expose control of these facilities, it's a very easy step to then do something like this example. So this is real. Once you are hooked into the compiler, and once you find a way to expose that capability in an easy to understand kind of pseudo-human language that non-compiler engineers can take advantage of, you can let other people start to tell the compiler what you want to happen. and more importantly, how you want the compiler to respond to vulnerabilities or issues that it finds, and or how you want the compiler to correct them. So here's a real example. In our case, this is a very active area of work for us right now, the team that I'm working with, is building up this kind of direct control capability for any user straight into the just-in-time compiler train. We get a call from a customer. This vulnerability, this was last year. Customer they're running around and their hair is on fire. Got a call from the platform and infrastructure folks, and they said security has just come down on them. They have been notified of this particular denial of service vulnerability. For some reason it was important inside this customer. We don't know which applications are affected. We don't know how to find them, but we've got to do something. What can you do? Okay? So in 24 hours, when you have the kind of controls you'll see on the next slide, these are the kind of things that you can start to get the compiler to do. The vulnerability in question was the absence of a bounds check on the initialization of a variable of that class. The consequence of that bug was that you could put in a particular value, integer value, and if it was above a certain threshold, it would kick a loop into running very significantly longer, and hence you could use that to create a denial of service attack. The grey box at the bottom of the screen is a picture of the patch file, the diff file, the change set, committed to the trunk of the Apache source code repository to fix that vulnerability. One line, in this case, a one-line fix. Trivial stuff, simple stuff. The bounds check wasn't being performed. They went ahead and added the bounds check, and everybody was happy. But what that means for organizations is in some ways, that's only 10% of the solution. Because 90% of the solution for most large organizations is how on earth do I get that to every application in my state and do so in a timely manner. Because the Apache guys might be able to fix this in a day or in 2 days, but then that becomes a new jar file artifact in the case of this particular issue. You've got to then distribute that artifact. That artifact's then got to be, you've got to take the application out of service, you've got to load in the new artifact, you've got to go through some kind of UAT, QA, acceptance testing, whatever it might be, process that's appropriate for you. And then finally, if you're lucky 3 months later, you've actually got that in prod. So having direct controls into the just-in-time compiler, here's an example of the kind of things you can do. Now this is a very simple example, using in this case a very crude rule grammar. But it's kind of like pseudocode. You can kind of get what's going on. Basically, you're talking to the just-in-time compiler. And you're saying, hey, Mr. Compiler Man, I have got a rule. It is a virtual patch for CVE, blah, 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 blah. It affects this particular class, this particular method, at a particular, in this case, at a write event that occurred in that method. Go and find me that class, if it exists. If it doesn't exist, it'll not. It'll do nothing. Go and find me that class, and if a condition is true, I want you to generate a security alert, a warning, that I'm about to apply a virtual patch, and then the action that I want Mr. JIT Compiler Man you to do for me is add a bounds check. Pretty simple concept with this consequence. The grey box at the bottom is the real source code fix from the Apache developers to fix that vulnerability. The grey box at the top is an example of a virtual patch rule communicated directly to the just-in-time compiler. They both perform or deliver exactly the same functional effect. Identical. No difference. One of them requires you shutting down your application, downloading a new binary artifact, going through a repackage, redeploy, rebuild, integrate and distribute process, and the other, just reload the rules. No interruption to service. The application isn't stopped. The application isn't shut down. The application isn't restarted. It can be in the middle of servicing 1,000 concurrent requests, and the JIT compiler, because that's what JIT compilers do, great, and compiles it in. Not even a garbage collection pause. So real example of using that kind of virtual patching control and language delivered to a real customer. We delivered that rule in less than 24 hours. Within 48 hours, all apps were patched. And they could deploy that blind, and they didn't need to care whether the app actually ran Tomcat or not, as an example. So that's it. I'll get to questions in a sec. I can see hands going up, which is great. My closing comment. The security community needs to start talking to the runtime guys. They have been out in the cold, but they have a lot of value to bring to solving security and application security problems. And now, 2016, 2017, we are starting to see those two communities come together. And my prediction is when that happens and the runtime and the compiler community becomes entwined with the security and application security community, we will see a step change in the way that we can collectively respond to security problems, security vulnerabilities, security exploits and incidents, and I guess, make the world a better place.